So the stronger the intermolecular forces, the more energy is needed to break them. And here we have enthalpy of vaporization, which is just the amount of energy it takes to go from a liquid to a gas. So we talked about how, that does need quite a bit of energy to go from a liquid to a gas. And here's just some examples. And you don't need to memorize these numbers or anything, just to show you, what it looks like pretty much. So helium's a gas and argon's a gas. Helium's much smaller and it has weak intermolecular forces, and we can see that with the enthalpy of vaporization. So 0.0828. And then argon is also a gas, but it's a little bigger and the intermolecular forces are stronger, so its enthalpy of vaporization is bigger. Then methane has a larger enthalpy of vaporization because it has stronger intermolecular forces. So as I go down here, they're almost increasing. We have benzene in a weird spot, so benzene really should go in between ethane and methanol. But as those intermolecular forces are getting stronger, then the more energy is needed to break those interactions. So that's all I really want you to know with enthalpy of vaporization is the higher the enthalpy of vaporization, the stronger those intermolecular forces are. So you won't be calculating anything with enthalpy of vaporization, but if I gave you a list and said which one has the strongest intermolecular forces, then you would just pick the one with the biggest number. Okay, next property we're going to look at is vapor pressure. So anytime you have a gas, you have a pressure, right? We talked about that in chapter 10. Those molecules are moving, making contact with the container walls, and it creates pressure. So when we have a liquid and the molecules have enough energy to overcome the intermolecular forces, then they're able to move from liquid phase to gas phase. And so anytime, again, we have those gas molecules, we're going to get pressure. So this is just vapor pressure because we have those molecules evaporating. Okay, so let's say we have a closed container and we have ethanol in this container. So the molecules begin evaporating. You can see in the second picture there. So they're going to bounce around. They're going to hit the container walls, but they're also going to eventually hit the liquid. And when those molecules hit the liquid, they go back into the liquid phase. So we have molecules coming out, they're evaporating, and then we have molecules being condensed and going back into the liquid. So when those two rates are equal, so just write this out here. So rate of vaporization or evaporation when that's equal to the rate of condensation, then we get a dynamic equilibrium. Excuse me. So this can only happen with a closed container. This wouldn't happen with an open container. Okay, so we get this equilibrium vapor pressure built because we have those rates are being equal. Okay, now if we increase the temperature, that's going to affect our vapor pressure. So if I'm increasing temperature, I'm giving those molecules more energy, which means they're going to move faster and they're going to be able to break away, break those intermolecular forces. Okay, so here we have just a graph representing that. So the blue line is the lower temperature, the red line is the higher temperature, and then the dash there on the right represents the minimum amount of kinetic energy needed for those molecules to move from liquid phase to gas phase. So you can see some of the molecules in the lower temperature have enough of that energy to move out of liquid phase into gas phase. But more molecules have the energy to be able to do that at a higher temperature. So increasing temperature is going to increase the amount of molecules that are evaporating and it's going to increase our vapor pressure. So we'll have more molecules in the gas phase, which is going to increase our vapor pressure. So know that relationship between temperature and vapor pressure. Okay, so here we can look at the vapor pressure compared to the intermolecular forces. So all of these liquids are volatile. So I'll write this down. So volatile. So that just means a liquid evaporates easily. Okay, so looking at these liquids and their vapor pressure numbers, we can see that as the vapor pressure increases, let's just look at the first one at 0 degrees Celsius. So if vapor pressure is increasing, that means our intermolecular forces are decreasing. So the stronger the intermolecular forces, the more difficult it's going to be for a molecule to move from liquid phase to gas phase. So water at 0 degrees Celsius has a vapor pressure of 4.6. And then benzene is 27.1, methanol 29.7, and then diethyl ether is 185. So that means water has the strongest intermolecular forces because at the same temperature, it has a low vapor pressure, which means it's difficult for those molecules to move from liquid phase to gas phase. But then if you look at diethyl ether, it has a very high vapor pressure because those molecules can easily move from liquid phase to gas phase. And you can see as we increase the temperature, it's still, that trend remains the same. Next is boiling point. So boiling point goes along with our vapor pressure because the definition of boiling point of a liquid is the temperature at which its vapor pressure is equal to atmospheric pressure. So there's two definitions here, boiling point, and then normal boiling point is the temperature at which the vapor pressure is equal to 760 torr. So you need to know the difference between those two. So the higher the boiling point, the stronger the intermolecular forces, right? Because if I need more heat, more energy to be able to break those intermolecular forces, it means they're pretty strong. So if I have a boiling point of, we'll just use water as an example, 100 degrees Celsius compared to a boiling point of 60 degrees Celsius, then water has stronger intermolecular forces because it had to get all the way up to 100 to be able to start breaking those intermolecular forces. Okay, so boiling point of a liquid, this changes based on atmospheric pressure. So if you've ever been in the mountains and had to cook something, they usually give you, directions for cooking in the mountains or directions for cooking at sea level, because as you get higher, the atmospheric pressure is lower. So that means your water is going to boil at a lower temperature, and it's going to take longer for something to cook. So just for example, let's say you're boiling an egg, and normally at sea level, it would boil at 100 degrees Celsius, but in the mountains, it's going to boil, 90 something. So it's not as high of a temperature, and so it's going to take longer to boil, or not to boil, but to cook. Okay, so going higher up lowers the atmospheric pressure, which also will lower the boiling point. Okay, so just to give you an example here of how higher the boiling point, the stronger the intermolecular forces. Okay, water here to the very right has the highest boiling point. It also has the strongest intermolecular forces. Okay, then ethanol has a boiling point of 78.3, so that means it's weaker, has weaker intermolecular forces. And then the weakest is diethyl ether. at 34.6 degrees Celsius. So we could put, intermolecular forces strength based on the boiling point in order, if we're just given those boiling points.